Before getting into automotive cybersecurity assessments, I want to explain the technical perspective I bring to this work. My background is in post-production vehicle platform triage and validation. That means I work directly with vehicle behavior after software has already been deployed. I am not looking at designs in isolation. I am looking at how vehicles actually behave in the field. In this role, I analyze ECU behavior, gateway behavior, over-the-air update execution, diagnostic responses, security state transitions, and system logs. The goal is to confirm that systems behave as expected and to identify deviations that introduce safety risk, security risk, or compliance concerns. Working in this environment has fundamentally shaped how I approach automotive cybersecurity. I do not start from theory alone, I start from observed behavior, real system responses. Over time, I have learned that a security control only matters if it is actually enforced by the vehicle, and just as important, that enforcement must be provable through logs, diagnostics, and system state. Because of that, when I apply cybersecurity frameworks such as STRIDE or MITRE ATT&CK, I do not treat them as abstract modeling exercises. I treat them as engineering tools that must map directly to real vehicle behavior. Let me explain what that looks like in practice. When I use STRIDE, I begin by defining system scope and trust boundaries. This includes electronic control units, gateways, communication paths, diagnostic access points, and back-end interactions. STRIDE then helps ensure that threat analysis is systematic rather than ad hoc. Each STRIDE category is translated into concrete validation questions. For spoofing, I ask whether an electronic control unit or service can be impersonated, whether identity enforcement is observable through authentication failures, diagnostics, or gateway behavior. For tampering, I examine whether firmware images, configuration data, and update packages are protected, and whether enforcement is visible during update execution and validation steps. For repudiation, I evaluate whether the platform generates sufficient logging and evidence to reconstruct what actions occurred, and whether those records can be trusted. For information disclosure, I assess whether diagnostic services, telemetry, or data channels expose information beyond intended trust boundaries. For denial of service, I look at whether update flows, diagnostics, or inter-unit communication can be disrupted in a way that degrades availability or function. For elevation of privilege, I examine diagnostic session handling, security access routines, and configuration controls to determine whether higher privileges can be obtained improperly. STRIDE helps identify where control should exist. It does not by itself prove that those controls work. That is where adversary-based reasoning comes in. Once a risk area is identified, I use MITRE ATT&CK concepts to reason about how an attacker would realistically attempt to exercise that weakness. This includes understanding potential attacker paths, misuse of diagnostics, lateral movement gateways, or abuse of update mechanisms. The focus is not on hypothetical attacks. The focus is on feasibility, observability, and detection. At this point, validation becomes the most important part of the assessment. I treat system logs, diagnostic responses, and state transitions as security evidence, not just troubleshooting output. If a control cannot be validated through observable behavior, then it is functionally unverified regardless of design intent. To improve consistency and scalability, I have designed tooling that supports this assessment process. These tools analyze logs and diagnostic artifacts, correlate security relevant events, and map observed behavior back to identified risks and controls. The goal is not automation for its own sake. The goal is to reduce human error, improve repeatability, and preserve defensible evidence. This approach aligns naturally with automotive cybersecurity standards such as ISO SAE 21434, which emphasizes cybersecurity engineering and validation, and with United Nations Regulation 155, which requires manufacturers to demonstrate that cybersecurity risks are managed across the vehicle lifecycle. Frameworks provide structure, validation provides assurance. Ultimately, automotive cybersecurity assessments are not just about frameworks. They're about engineering judgment, system understanding, and evidence. Real assurance comes from validating how vehicles actually behave and from being able to prove that behavior. With that foundation, I want to walk through how these assessments are performed in practice and how structured frameworks, validation, and tooling come together to support real automotive cybersecurity engineering. This walkthrough reflects how I apply structured frameworks, how I validate controls using real vehicle behavior, and how evidence is produced at the engineering level. I will describe this as a sequence of steps because cybersecurity assessments are not a single activity, they are a workflow. Step 1 defines system scope and boundaries. Every assessment begins with scope. Before identifying threats, I define exactly which vehicle systems are in scope. This includes identifying the relevant electronic control units, gateways, communication paths, diagnostic access points, and any back-end or cloud interactions involved. At this stage, the goal is not to find vulnerabilities. The goal is to understand how the system is constructed, how components trust each other, and where boundaries exist. If scope is incorrect, everything that follows will be incomplete. Once scope is defined, I apply STRIDE to ensure systematic threat coverage. STRIDE is used here as a classification tool. It helps answer the question, what categories of risk must be considered for the system? For each STRIDE category, I identify where controls should exist. For example, where identity must be enforced, where integrity must be protected, where logging must be present, and where access must be restricted. At this stage, I am identifying required protections, not proving that they work. Step 3, translate threats into validation questions. This is a critical transition point. Instead of stopping at threat identification, I translate each STRIDE category into validation questions. These questions are intentionally practical. For example, if identity enforcement exists, where do I see it fail? If update integrity is enforced, what evidence proves that? If access is restricted, what happens when access is attempted incorrectly? Step 4, reason about realistic attack paths. Once risks and validation questions are defined, I apply adversary-based reasoning using MITRE ATT&CK concepts. This step focuses on realism. I ask how a threat would actually be attempted, what steps an attacker would need to take, and what system behavior would change as a result. The purpose is not to simulate attackers, but to understand feasibility, exposure, and detection opportunities. This helps prioritize which risks deserve deeper validation. Step 5, validate controls using vehicle behavior. This is where assessment becomes evidence-driven. Controls are validated using observable system behavior. That includes examining system logs, diagnostic responses, update execution traces, and state transitions. I'm looking for confirmation that controls are enforced and that failures produce expected traceable outcomes. If enforcement cannot be observed, then the control cannot be considered validated. Design intent alone is not sufficient. Step 6, treat logs as security evidence. Logs are not treated as secondary artifacts. Logs must show that controls were exercised, that failures were handled correctly, and that system behavior can be reconstructed if needed. This is especially important for compliance and audit readiness. Step 7, use tooling to improve consistency and scale. To support this process, I designed tooling that assists with validation and analysis. These tools help parse logs, correlate security-relevant events. The purpose of tooling is not to replace engineering judgment. The purpose is to reduce human error, improve repeatability, and ensure evidence is preserved consistently. Step 8, align findings with standards and regulation. Finally, findings are aligned with cybersecurity standards and regulatory expectations. This includes demonstrating that risks were identified, controls were validated, and evidence exists to support conclusions to compliance requirements. This alignment connects engineering work without reducing assessments to paperwork exercises. This is how automotive cybersecurity assessments work in practice. Frameworks provide structure. Adversary reasoning provides realism. Validation provides assurance. Evidence provides defensibility. The assessment is complete only when vehicle behavior, security controls, and documented evidence all align. That is the standard I use when evaluating automotive cybersecurity systems.